Please go
Good,
ahead.
good. So, yeah, as I've introduced, I'm Matt. I'm now a fourth-year PhD student at University of Hertfordshire, working with Jim Geach, and for this work also Professor Jackie Kobayashi. So I'm going to be talking about the CO isotopologues and whether or not they point to a top-heavy IMF within starburst galaxies. So a brief outline of what I'm going to talk about. What is the IMF and why should we care about it? Why I think the CO isotopologues and the IMF are linked. And because, as I said, it's a multidisciplinary conference, I'm going to give a brief background of sort of SMGs and ULERGs, and then go into the sort of, the SMG that I'm working on, the lensed sort of high LERG, about redshift 2, and then just conclude with a bit about what future work we're going to be doing with 9009, which is the galaxy, and then just conclude. So to start with, what is the IMF and why should we care? So the initial mass function, or the IMF, basically just tells us the initial distribution of the masses of stars during star formation. And typically we parameterize it with power laws or log normal in some other cases. This is really important in both the local universe, if we're looking sort of in star forming regions, as well as for pretty much any extragalactic observations. If you're deriving many properties such as the star formation rate or the stellar mass and things like that, an IMF is assumed in these calculations. So if it varies from that, from the sort of one you assume, then all of your properties would have to be revised. And of course, all simulations, especially cosmological, will all assume an IMF within them. So typically, there's a couple of different IMFs that get used. So Krupa 2001 and Chabrier 2003 are probably two of the most common, with salpeter, of course, being the standard IMF that most people would have heard of. So it's, these IMFs are the standard ones, but also you do find some variation. So within Milky Way simulations, both the Krupa 2001, which has a high mass slope of 2.3, and also an older Krupa with a high mass over 2.7 is also occasionally used, depending on the sort of models that are, what simulations are there. So I've put a table down in the bottom left with some of the parameterization. It's not too important, but I can go back to that if anyone needs to see it again. So why are these various IMFs important between them? So I've put at the top here the star formation rate you obtain from them if you assumed them with your, in the case of starburst galaxies, with our IR luminosity. With the Krupa 2.3, if you had a star formation rate of 1,000, you can see they vary significantly between them, with the Chabrier and Krupa 2.3 being fairly similar, but this steeper Krupa having a factor of 3 more in star formation rate. So that's quite important, and it will be important in a minute, because it ends up leading to two subtly different questions when we're talking about our starbursts. The first question is the IMF within starbursts different from that of the Milky Way on sort of galactic scales? And the second would be, do we need to refine our galactic properties because it differs from the IMFs we assume there? If the Milky Way IMF is the same as the one we're assuming in galactic properties, then these become the same question. So I'll just move on to a bit about why we think CO isotopologues are linked. So the CO isotopologues we're working with are the 13CO and the C18O. The ratio between these should be dominated by the ratio between 13C and 18O. So if you measure the ratio between the isotopologues, you can get a sort of abundance ratio between 13C and 18O. The reason this is linked to the IMF is due to the different production routes of these two different isotopes. So 13C is primarily formed in low mass to intermediate mass stars, so between about 1 and 4 solar masses, and 18O is primarily formed in high mass stars. So quite simply, you can sort of imagine it's a rough proxy for the ratio of massive stars to low mass stars. Though this ends up being complicated, of course, because different stellar lifetimes and also various star forming regions occurring at different ages. So one thing as well, sorry to mention, is that the ratio can vary by greater than order of magnitude if you change the IMF, which is why it's thought potentially be a sensitive tracer or indirect tracer of the IMF. As I said, it's a bit complicated with various stellar lifetimes and star forming regions having different ages. What you need to really address this is state-of-the-art chemical evolution models. So we use the models that you can still see in the Kobayashi et al. 2020. So they use up-to-date yields, and you can sort of change the IMF within them and the various star formation histories, and it be able to help us track the isotope ratios over time. So previous work has been done on this. So Zhang et al. 2018 used a simple starburst model, so a single starburst from redshift 3 to 2. So building up the stellar mass, and then looked at how the ratio changed over time. As you can sort of see from a bottom heavy IMF here, all the way down to sort of a very top heavy Bolero, you get quite a wide range of resultant ratios. Bringing back, I said about the Milky Way IMF, with the models they use here, which come from Romano et al., their best fit IMF for the Milky Way as a whole, based on their chemical evolution models, is the steeper 2.7 Krupa. So we do need to keep that into account when we're sort of answering some of the questions I mentioned earlier. So submillimeter galaxies, as many of you know here, are incredibly bright in the submillimeter wavelengths, which is where they get their name. They have inferred star formation rates up to the thousands of solar masses per year, assuming a sort of Chabrier IMF or the 2.3 high mass SOPA I mentioned earlier. They tend to be optically faint due to vast quantities of dust, which are occurring from this intense star formation occurring in these galaxies. And their distribution peaks at about a redshift of 2, and then is a significant fraction of the star formation at this epoch. The dust is also why we're looking for this different way of trying to constrain the IMF. So standard methods use either optical or UV wavelengths to try and constrain the IMF. Of course, when you've got a significant amount of dust, this is significantly going to affect that. So you want a dust-free, sort of extinction-free measure of the IMF. Also, of course, we're at high redshift, so number counts of stars is incredibly infeasible to even attempt. So the galaxy in particular I'm mentioning is 909. It has a few names in the literature, so it's also known as the red radio ring. And here is a sort of Hubble image of it. You can sort of see it's a quite simple lens with a main elliptical galaxy at the center and a sort of smaller companion in the north. And from this, we have managed to get a source plane IR luminosity. We've got a well-constrained lens model, and it is approximately 10 to the 13 solar luminosities, or about 1,500 solar masses per year, assuming a sort of a Chabrier or a Krupa IMF. It's a very gas-rich galaxy. So from C1 emission, we've inferred a gas mass of around 10 to the 11 solar masses. This is similar with to the results from low JCO lines. And the joy of using sort of lens galaxies is the flux is magnified by a factor of about 15. So we can study emission lines such as the isotopologues, and also potentially go on obtain data on scales unobtainable outside sort of local galaxies. So back in cycle 7 now, so a few years ago or a couple of years ago, we got an ALMA spectral scan. So due to the distance between the main CO line and the 2 isotopologues on the left, it was not feasible to sort of do individual tuning to both of them. So we managed to get a whole spectral scan, which future work will focus on many of the other lines, but just in particular for this work, it's the CO and the 2 isotopologues just to the left. So here are the sort of spectral lines, as you can sort of see. The main CO 5 to 4, which is panel A, is incredibly bright. And as such, we've used this as an empirical template, so to, in effect, decompose these two slightly blended lines, the C18O and the H218O. And you can sort of see by looking at the sort of overlays that the line profiles of pretty much all of the lines in the spectra as well are all very similar and dominated by the sort of rotation of the galaxy. So the question is a top-heavy IMF needed to explain this ratio? So we observe a ratio of the 13CO to C18O of about 1.5, 1.6. This is consistent with previous observed ULERGs and SMGs, but an order of magnitude below that of local spirals, which tend to have a ratio of around between 7 and 10. What we need for this is we've ran two different model groups. So one which doesn't include stellar rotation. This is similar to the Zhang 2018 models, and one which includes the effect of stellar rotation. So this will be including sort of large contributions from Wolf-Rayet stars and similar classes. As you can see on the left-hand panel, which is the no rotation set, we get a similar sort of relationship was found with the Zhang. So the more top-heavy, which is top-heavy's top left panel, and then the bottom-heavies on the bottom panel. You can see as you go more top-heavy, the ratio decreases, but you can also see we are still consistent with Krupa 2.3 IMF. The right-hand side panel, which is the rotation panel, you can see this relationship found in Zhang is completely gone. This actually occurs due to the 18 oxygen and 13C no longer being limited in the same way to intermediate mass and high mass stars. So you end up with a far more complicated mix of stars. And due to that, you can't really, with the ratio alone, constrain what IMF is used, at least for sort of standard IMF or top heavy. The more bottom heavy IMFs are still very much clustered together, so you can sort of rule them out with these wide range of model sets. So, sorry, I did forget to mention the model sets are a wider range of star formation histories. And here is the star formation timescale. So we have a very similar starburst to the Zhang models, but we also include extra little bursts as gas in fours, and also vary the timescale to try and take into account a wide range of possible sources as well. Okay. So there we go again. I'm just saying it's consistent and sort of there. So just to finish with some future work, we not related to the IMF, but we have got a Cycle 8 proposal accepted, rated, which is to look at the dust polarization. So potentially, if we detect this, we will be able to measure the magnetic fields in a sort of SMG for, I believe, the first time. Also, we've got the spectral scan other lines, which also trace a wide range of conditions. Many of them are dense gas traces, like the CN and HNC. But that's sort of part of our future work, and hopefully we can sort of constrain many of the conditions within this source. And finally, some Almond Cycle 9 proposals and data, hopefully, if it's accepted. We're hoping to sort of push the study of this source by going to very high resolution. Currently, we've got 300 milliarc second data, but we can push this further and hopefully reach scales in the source plane of about 100 parsecs, so reaching GMC scales in the local universe. And here's the sort of the spectra. And finally, just conclusions. So we have detected two of the CO isotopologues, 13CO and C18O. We observe a ratio consistent with other SMGs and ULERGs. We find that the ratio is consistent with standard IMF used in deriving galaxy properties. So galaxies forming stars at around 1,500 solar masses a year seem to be a sort of real phenomena. But we also find that the inclusion of rotation breaks that nice IMF isotopologue ratio relation. And to really constrain the models to get a more robust prediction out of those with the rotation included, we need something like the star formation history or metallicity, which are quite difficult to sort of constrain in these sort of dusty systems. I'll finish there, and has anyone got any questions?
Thank you so much. This was a really interesting talk. Katrina, are there any questions coming?
Yeah, there's actually several from one person. So I think I will just do them one by one so you have a chance to remember what I said. So the first one is, have you considered the optical depth of the 13CO?
So we haven't. So to really look at that, so I know there is some arguments of whether or not 13CO will be optically thick. Really, to look at that, we would probably either need some sort of higher resolution data, but also multiple transitions of 13CO. So that is one of the options for a future AML proposal, to try and target multiple different 13CO and C18O transitions to try and see if there is any optical depth there. But one thing to note is that, of course, does drive the ratio to closer to 1, which would, if optical depth is significant for 30CO, that increases the ratio and would actually keep it consistent with the standard IMFs.
Okay, then the second question is, what about the age effect on the isotope ratios? We still do not fully understand the 18O reaction rate, and the young starburst may also reproduce a low 13C18O. SMGs may experience recent merger events, so they might be very young, the age of the starburst.
Yeah, so the starburst part, so we are with the chemical evolution models, the ages of these things are taken into account. So the various stellar ages and when the star formation occurred, these are taken into account in the models. The young starbursts, of course, that's with the, sorry, let's see if I can go back. You can sort of see a huge variation in the ratio at the start. That's due to the initial starburst occurring, going down. Various starbursts will lower it, of course, because massive stars produce that. But of course, the ages of the stars would be included in the models. So, and we see it sort of, sorry, I'm sort of fudging that. They're included within the sort of models. So you should be able to take that into account if you use the right star formation histories, of course.
Okay, and there's another comment about the modeling. The chemical fractionation might greatly increase the 13CO, C18O in starburst environments, so the actual elemental isotope ratio might be even lower. Okay.
So yeah, I can't off the top of my head sort of remember the exact chemical fractionation, but my understanding would be my understanding was it wouldn't be significant in some of these SMGs, especially the sort of difference with the C18 and 13CO. But I'd have to sort of look up, and I should be able to write it in the Slack later, sort of the response to that.
Okay, there's another question about your upcoming observations, I think. So is there particular properties that you plan to constrain for the dust polarization data?
So we're hoping, we've put in for a range of resolutions. So depending on that, what we get out of that would depend on what we'd be able to do with it. Due to the sort of lensing and stuff, and we've got quite a well-constrained lens model, we're hoping maybe to sort of, at least first, is to get a detection. If we can get a detection of the magnetic fields and sort of get a rough idea of the strength of the magnetic fields, we would then be able to go back to high resolution and sort of map the magnetic fields across the galaxy. That's the hope. Sort of the magnetic field strengths and directions of the fields.
Okay, and there's one last question about C17O. Did you have that in your frequency range? And if yes, do you have a detection or non-detection, and does that mean anything?
So I believe it was in the range. We haven't got a clear detection of it. I don't think C17O has been detected in SMG. I think there are also about order of magnitude, it tends to be an order of magnitude fainter than even the 13CO or C18O. So I'm not entirely sure if we would have we shouldn't really expect to find it. However, there are also, my understanding with the chemical evolution models, there are still some issues to be sort of ironed out with the underproduction of 17O in many of these models. So I'm not sure if we would be able to really add anything at the moment with that detection.
Great, thanks.
Thank you.
All right. Thank you so much for the excellent talk and the answers.